I thought you'd all be talking to your friends. That's all right. So here's how I did this one. I immediately do this cosine squared x thing, but it's being squared again. So cosine to the 4, of course, is the same as cosine squared x squared, right? And then I'm going to use that first formula up there. 1/2 1 plus cosine 2x squared, right? I hope that's how you started it off. And then we should, what do you want to do next? Anybody work this one out?
Get rid of the square, like expand it.
Yeah, expand this thing with the square by doing the FOIL. So this 1/2 is going to get squared and turn into a 1/4. And actually that can move all the way outside the integral if you like. Or of course you could keep it sitting on as a coefficient inside. But anyway, when I do the FOIL there, I get 1 and then 2 cosine 2x and then cosine squared of 2x. Like that. That's the FOIL. What'd you do next? Yep.
You made the cosine squared 2x into like another identity.
Yes, do that first formula again, this one up in the corner, but this time applied to cosine squared of 2x, and it will turn into some kind of cosine of 4x there. So I got 1/4 out here, integral 1 plus 2 cosine 2x plus, here's that formula again, 1 plus, now it says cosine 4x, like that. Maybe I will distribute that 1/2 in there. It's not a big deal, but it's going to be 1 plus 2 cosine 2x plus 1/2 plus 1/2 cosine 4x. And now we can just, it's a bunch of stuff added together. We can just go down the line and do the integral each time. Something looks different. I wrote it differently on my paper, but that's fine. So I'm going to say 1/4 out here. And then integrating term by term now. 1 becomes x. 2 cosine 2x is a 2 there, and then 1/2 cosine 2x, sine 2x. Here I'm using this formula that said integral cosine kx is 1/k sine kx. All right, so this, which was cosine 2x, now becomes 1/2 sine 2x. And then I go plus 1/2 becomes 1/2 x, plus 1/2 cos 4x, just like before, is going to be 1/2 times 1/4 sine 4x. Like so. That's how we do it. I hope you got something like that. Unfortunately, I would consider this to be an easy one. I wouldn't call that easy, but as far as these go, this is an easier type one of these kinds of problems. They can be a little bit trickier than that. All right. I would say, as for like what's going to be on the quiz, I would say you should expect one at this level, just because I don't want you to spend all afternoon doing it. They can take a long time to do the harder ones. Anybody got questions about that? This is what the book refers to as trigonometric integrals. They are integrals of sine and cosine multiplied together with powers, that kind of a thing. All right. And I don't have anything more to say about this section. I would like to begin talking about the next section, which has a similar sounding name and, in my opinion, is not easier. It might be harder. This is what the book calls trigonometric substitution. So this is another batch of fancy tricks for doing certain types of integrals. This one is, in my opinion, a great deal less obvious what you should do. And I'm not saying the other one was obvious, but the other one is about using these formulas basically to do sort of simple tricks. The trigonometric substitution, in my opinion, is a more sophisticated idea, and it involves doing what I would describe as very weird U substitutions. So I thought I would start with just a very brief and sort of review of really simple u substitutions, just to make sure. I know everybody is good with u substitutions in general, but before we talk about these trigonometric substitutions, let's just talk very briefly about simple u substitutions. Simple u subs, all right? So for example, and with I'm gonna concentrate a little bit on the integration boundaries in a definite integral. So the integral from 0 to 3 of e to the 2x dx. There's no funny business here. What would you choose to be the u if you were doing a u substitution here? 2x, yeah, so I go u equals 2x. The du then is 2 dx. Now, the way that I typically do a u substitution is I sort of ignore the boundaries until the very end. So that way would look like I go, this is the same as integral e to the u times 1/2 du. I pull the 1/2 out, 1/2 integral e to the u. Do the integral, I get e to the 1/2 e to the u. And then I plug the original variable back in, and then I evaluate at 0 and 3. And my final answer is 1/2 e to the 6 minus 1/2 e to the 0. All right? So this is the way that I would usually do this kind of a substitution. Now, some of you in high school may have learned to change the integration values. So we can also, and actually in this, for most cases, for most purposes, it doesn't really matter how you prefer to do it. Although in this section that we're about to do, it is important to at least understand a little bit about how to do that, changing the value. So I'm going to say, or you could change the boundary values. I know some of you, this is already how you like to do it. Maybe some of you have not seen doing it this way. It's not hard, it's just you have to know how to do it. So that one would look like, I had the same thing. I begin like this, and I choose the u to be 2x as before, then the du is 2 dx. And I'm going to rewrite this. It turns into integral e to the u, but here's at times 1/2 du, just like before. The difference is I'm going to actually put numbers here and here, which represent values of u. So the u values of the endpoints. Well, if x equals, so they are 0 and 3, right? X equals 0, x equals 3. How do you find the appropriate u values? I can just sort of plug these numbers in to this formula, u equals 2x. So this will say u equals 2 times 0, which is 0. And this one, u equals 2 times 3, which is 6. So I'm using that little formula, u equals 2x, to calculate these values here. And then I can put those there and there. So if you do it this way, you are changing the values up front, and then you're never going to replace the x's at the end. You're just going to plug those values in for u. This is just a different way of doing it. So now when I do the integral, again, I will get 1/2 e to the u. This time plugging in 0 and 6, and I get 1/2 e to the 6 minus 1/2 e to the 0, which is the same answer as before, as it should be. These are just two different ways of writing out the same procedure. All right. Anybody have any questions about that? I hope that this seems okay to everybody, because I'm about to do something that's a variation on that, but a little weird, which probably you have not seen this kind of thing before. This is what our book calls inverse substitution. I'm going to do the same problem again. 0 to 3 e to the 2x dx. Now, the idea behind this is a weird idea, and in this particular example, I would say there's no good reason to do it in this way that I'm about to do. But in the examples we're about to do, it becomes more important. In this case, I think I want this up here to be u. What does that mean x has to be? In order for this to end up being u, x should need to be 1/2 u, so that it cancels the 2 there. So the idea here is you say what x is, and I say x equals 1/2 u. Rather than an ordinary u substitution, you usually think of as you look for u here, and then you say what u is. But in this case, I look at the x, and I realize x is next to a 2, and this will become simpler if the x actually had to have 1/2 as part of it. And so I make x equal 1/2 u. It's the same concept, but it's sort of written in a stranger way. All right? Anyway, if x is 1/2 du, we can still do the rest of the substitution. Can anyone say, what's the dx? You're going to take the derivative. 1/2 du, would you say? Yeah. And so this we can plug directly in, and it becomes e to the 2 times 1/2 u. I plugged in for x. And then the dx is 1/2 du. And then as before, we can calculate the appropriate u values. And this is a bit of a pain, but when x equals 0 here, that means that using my little formula, x equals 1/2 u, it means 0 equals 1/2 times u. And I can solve this for u. 0 equals u. Oops. Sorry. I'm plugging in 0, and that allows you to solve for u for the first value. And then I also can plug in for 3. X equals 3 means 3 equals 1/2 u. And this I can also solve for u by multiplying the 2 over there, and it says u equals 6. 6 equals u. So this integral is now 0 to 6. All right. This looks weird. It's really the same thing, but written kind of backwards somehow, in a strange way. Anyway, to finish the integral, I would pull the 1/2 out of the integral. Inside the exponent there is just going to be e to the u du from 0 to 6. And then the rest of it goes like you expect. 1/2 e to the u evaluated at 0 and 6. 1/2 e to the 6 minus 1/2 e to the 0, right? So the book calls this inverse substitution. It's really the same idea, only instead of sort of like, it's really just right here. Instead of saying what u is, you say what x is, which is a little strange. Any thoughts about that one? The big thought in your mind, the big question is, why would you ever want to do it this way? This is just like a more confusing version of this. And if that's your attitude, I say, I'm with you on that. In this particular problem, there's no good reason to do it this way. But the examples that we're going to do today involve weird substitutions like that, where that's the only way to do it. All right, so let's just try some simple tricks. So this is called trigonometric substitutions. I actually kind of really like the trig substitutions. I find them difficult to do, but I think it's really a cute little trick. I remember one integral from my youth when I first took calculus. This was one that I was presented with. Anybody know how to do this integral? You could say, do it with a trig substitution, that's how. But there's actually, this is usually like one of the first example integrals that people talk about when you learn what the integral is. This is hard to do with antiderivatives. Easy as an area. Easy, you'll have to take that with a grain of salt. But can anybody say, what does that represent as an area? Anyone know what that function looks like? So this, if you think of it graphically speaking, it's that, right? The graph of that. Does that look familiar to anybody? Maybe I could simplify a little bit by squaring on both sides, just because I don't like the square root.
Is it a circle?
It is a circle, yeah. It is, to be specific, the top half of a circle, because the square root, I used only the plus square root, not the minus. But this on a graph is the top half of a circle. This is a circle. with radius 1, right? Because of this 1 right here. And I'm looking at the area. The integral says 0 to 1. So I'm talking about this area here. Can anyone say what that area is? It's 1/4 of the full circle area. What do you think? The full circle area is pi r squared, right? And the r is 1, so it's pi. Pi times 1 squared. And so that shaded region is pi over 4. All right? The full circle area is pi. That is 1/4 of that, so this is pi over 4. So integral 0 to 1 minus x squared dx is pi over 4. This, I don't know if you ever thought about examples like this. This is somehow kind of shocking to me just from the point of view of doing integrals. Now, I did this by thinking of this in terms of an area, but if you were going to try to do this integral just by some kind of weird U substitution tricks or something, how could you possibly do tricks with that and end up with pi over 4? This is kind of crazy that the answer ends up being pi over 4. When you didn't begin with anything that resembles sines and cosines or anything like that. It's just a,
You do something with like cosecant because it's sine. It would be like
Cosecant.
1 over sine, like it's the inverse derivative of sine.
yeah, this might remind you of something about the derivative of the inverse sine is 1 over that. So maybe this has to do with, that's one way you could look at this integral and say, yeah, maybe that has something to do with the trig function somehow. But this is, the idea of the trig substitution is to actually do this without reference to the geometric argument, which is a little, this geometry is very touchy, right? Like if I changed, instead of 0 to 1, if I'd said 0 to 1/2, you're totally screwed at that point. Because you don't know how much area is just going up to 1/2 here, right? But if you know the trigonometric substitution tricks, then you can actually work this out without too much trouble. All right, so let's just try that one. This is actually a very easy example of a trigonometric substitution. 0 to 1 minus x squared dx. And we're going to do something like what I called before, like an inverse substitution. So I'm not going to look at this and choose something to be the u. I'm going to just turn x into something completely different. And my substitution is going to be x equals sine theta. So I'm turning the x into something else. Now, in order to make this, you could use a u if you like, although when we do these trig substitutions, we're basically always going to use theta. What about the dx then? Can somebody say? This is just,
Cosine?
yeah, cosine theta, d theta, right? And then we should also think about changing the boundary values. When you're doing this kind of inverse substitution, you really need to change the boundary values up front. There's not an easy way to plug them back in at the end. So we are going to change the boundary values. X equals 0. Remember, the way to do that is to plug in right here x equals sine theta. So I'm going to plug 0 for that and then solve for a theta value. So this will say 0 equals sine theta, which means theta equals, what's the theta which gives you 0? It is 0, yeah, sine of 0 equals 0, okay. And then we also have x equals 1, gives me 1 equals sine theta. And what's the theta to use for that?
Pi over 2.
I think that would be pi over 2. Yeah, of course there are other values, but pi over 2 is the one that makes sense to use in this case. All right, so when I change the integral into, it's not going to be a dx anymore, it's going to be a d theta. And those are the boundary values I'm going to use, 0 to pi over 2. So doing my substitution, it now is the integral 0 to pi over 2. And now immediately I'm starting to feel this pi over 4, right? Now I believe that this is actually going to make some kind of sense at some level. Inside, square root 1 minus x squared is just sine squared theta, right? And then dx becomes cos theta d theta. Like so. dx becomes cosine theta d theta. This is the old inverse substitution thing. Yeah?
How did you choose to change x to sine though, like not cosine? How do you know what to change?
Yeah, it's because this determines what x is. X is sine theta. So when I see x being 0, that means 0 is sine theta.
No, but like how did you choose the x and cosine?
Oh, because I know how the trick's going to work.
Oh.
So this is something we're going to talk about in a moment, about how generally speaking you... Yeah, this is a crazy choice if you don't know what's going on. But yeah, we'll talk about strategies for how to make those choices. Yeah, this is an excellent question. Can we finish the integral in any case? Anybody? This looks kind of like a nightmare, but actually we can do some business here. Any ideas? What I really don't like is the square root sign here.
1 minus, or cosine squared.
Yeah, 1 minus sine squared is cosine squared. So then I start to like it. All right? 0 to the power over 2 square root cosine squared theta times cosine theta d theta. And now the square root and the cosine squared can kind of cancel and give you just cosine. So it's 0 to the power over 2 cosine theta times another cosine theta. This is cosine squared, of course. 0 to the power over 2 cosine squared theta d theta. All right, that's all I can do for simplifying. What can we do with that? Yeah?
Do the 1/2.
Right, the old formulas that we were using at the very beginning. So this is now a trigonometric integral of the type that we did at the very beginning. So that we can use the old 1/2 whatever. So this becomes 1/2 1 plus cosine 2 theta d theta. And I think this is all going to work out, right? Pull the 1/2 out. That's how I like it. Integral 0 to the power over 2. And then what's inside? 1 plus cosine 2 theta d theta. This we can just integrate term by term. So I got a 1/2 on the outside. 1 becomes theta plus cosine 2 theta becomes 1 over 2 sine 2 theta. And then I'm going to plug in 0 and pi over 2.
Would it be negative minus 1/2 sine? Because this.
I don't think so. The derivative of sine is cosine. The integral of cosine is sine. It's a good objection to raise because I often get it wrong, but I think that's right. All right.
I have one question.
Yes.
When you set x equals 0 and x equals 1, like you're changing the bounds essentially.
Yes.
Would you need to put a negative because like the lower bound now becomes like the top, becomes like a higher number because pi over 2 is greater than 0?
No, because it was always like that, right?
Well, because
I put them in the same order. So
oh wait, x equals 1. Yeah.
0 was on the bottom.
But would you need to if it did become like a?
I would have. So you should maintain the same order from top to bottom. Yeah. And if you want to write in the other order, you would add a minus sign. Yeah. Okay, we're not quite done here. I want to get pi over 4. That's supposed to be the answer, right? So let's plug in now pi over 2. So this is a half. Pi over 2 plus 1/2 sine of 2 times pi over 2 is pi, right? And then minus 1/2. Plugging in 0. That's all going to be 0, right? So these are all 0. The first one, sine of pi, is also 0. And so I just get 1/2 times pi over 2. Pi over 4. It's satisfying to me to be able to do this without thinking of it as an area. Right? All right. Any questions about the basic method? The big question is, how are you supposed to know what tricks to do when? But that's, we're going to talk about that. But this is the basic setup here. All right. So there's a general principle here, and that is, if you see something that looks like that, a square root 1 over 1 minus x squared, you should try to change the x into a sine, because then 1 minus sine squared gives you cosine squared, and you can cancel the square root. So generally speaking, this is a general sort of a pro tip here. So generally, if you see square root 1 minus x squared, but generally actually it's, if you see something like this, it doesn't have to be a 1 there. It should be some number squared, which kind of represents like the radius of a circle. If you see something like that, then do x equals a sine theta. The example we just did had a equal 1, so that was a simpler case, but it's really not any more complicated if there's some other number right there. And then, of course, this means the dx is going to be a cosine theta d theta. Maybe I'll put this in a little box here. So doing the trig substitutions requires you to remember some of these basic tricks. And then you have to be able to do the, you have to be able to actually do whatever integral it is you end up with. All right. Let's try another one. I got a few more, and then I have some for you to try. This one looks a bit more complicated, but we're going to use the same batch of tricks. How about that? This one has no integration boundaries, which makes it a bit easier. We don't have to think about changing the values around in the middle there. All right. Knowing that this is going to be a trig substitution, we should just follow the advice in the box. What's the a going to be this time? 3, yeah. I see 9 there. I want it to look like a squared, so I'm going to do this here. X equals 3 sine theta. Dx equals 3 cosine theta d theta. Now there's also an x squared on the bottom. I don't know what's going to happen with that, but hopefully everything will work out fine. All right. So these are my x and my dx. We should begin by plugging stuff in. Up top, 9 minus x squared becomes 9 minus 3 sine theta squared. And on the bottom, x squared is just 3 sine theta squared. With a d, and then the dx becomes 3 cosine theta d theta. All right? The dx is important, of course. Don't forget to change the dx into a something or other with a d theta in it. And now we should try to simplify as much as we can. Any suggestions for simplifying? Yeah? Yeah, you can do the square root. I don't know exactly what you mean, but you can't just immediately do the square root because they're added together on the inside. Although you can do something with that. Yeah?
Can you like multiply sine, like can you multiply 3 sine theta and do like an identity to like, I don't know.
It's not that complicated. You could, first of all, let's just square this. This is like two things multiplied together. So I can square the 3 and also square the sine.
Yeah.
So let's do that. Is that what you meant?
Yeah.
All right. Then yes, you're absolutely right. 9 sine squared theta, like that, right? And on the bottom, do the same thing on the bottom. 9 sine squared theta. Over here, 3 cosine theta d theta. All right. Any ideas now? Yeah.
You could split it up so it's square root of 9 over the denominator and then minus.
No, you can't do that. When you have this like added together inside of a square root, that cannot be broken apart.
Never mind.
There's a yeah.
Sine squared trick.
Do the sine squared trick. Yeah. Just like we had before in this example, 1 minus sine squared inside the square root. We turn that into cosine squared. Now this is not a 1 minus. How do you deal with those 9s? Anyone?
Did you factor?
Yeah, I think you can just like pull the 9 out of the square root. Now it doesn't come out unharmed, but it comes out as a 3, right? This is the old. This is like, for instance, how you change root 8 into 4 times 2 in there, and then this comes 2 root 2, right? Remember this old trick? if you have a square multiple on the inside of a square root, you can pull it out of the square root, but it loses its square. So that 9 on the inside pulls out of the square root sign and becomes a 3. Because you can think of this as just doing the square root of the 9, but the rest has to stay like it is. 1 minus sine squared theta. On the bottom, 9 sine squared theta times 3 cosine theta d theta. I think actually at this point all the 9's cancel, or the 3's. I have 2 3's in numerators and a 9 in the denominator, right? So all of those 3's and 9's can go away, like that. And then, like he said, in the square root, I see 1 minus sine squared. I turn that into cosine squared under the square root. Oops. So this becomes square root cosine squared theta over sine squared theta, cosine theta d theta. That cosine in the top, it's just cosine, right? It's the square root of cosine squared, but that simplifies to just cosine up top. Cosine theta over sine squared theta, cosine theta d theta. This, if I write it all as one fraction, says cosine theta over cosine squared theta over sine squared theta. All right. And we are almost to the end here. What can you do with that? This is I would say, non-obvious trick, or this is maybe something that I would expect you to be able to look up if you found this on your homework. Cosine over sine is cotangent. So really this is cotangent squared theta, d theta. And doing some simple tricks at the end here. These are tricks that like I said, I would not necessarily expect you to remember this kind of thing on our quizzes or on a test, but cotangent is the same as 1 minus, it's the other way around, cosecant squared theta minus 1. That's because cosecant, they're equal. There's an identity about cotangent plus cosecant. And then, does anyone remember there's an integral, d theta. The integral of cosecant squared is negative cotangent, I think. That's what it's minus cotangent. So this is one of those sort of look it up type integral formulas. And then the 1 gives me a theta, all right? So the integral of cosecant squared is minus cotangent, and the integral of 1 is theta. And this is my final answer. Actually, not quite my final answer. One thing which we should do here, so the integral is done at least. There's an extra step. Now write it using the original variable. This is a bit of a pain. In a typical U substitution, this step is always easy. You just plug in at the end whatever the theta was. Like in this case, I just have theta, and I would replace whatever is theta. But in this example, because of the way we set up the substitution at the beginning, we don't actually have a nice formula for theta. Sorry, I'm going back. Here, right? X equals 3 sine theta. This is not a convenient formula for theta in terms of x. We need to write this as a formula, theta in terms of x. So I have x equals 3 sine theta. I want theta equals whatever in terms of x, right? Any ideas on how we could solve the first thing for theta? Yeah?
Can you divide by 3 and then do sine inverse?
Yeah, I like that. So this I say, first of all, sine theta equals x over 3, and then do the inverse sine. Theta is inverse sine of x over 3. This is how we rewrite using the original variable. So my final answer, this thing here becomes minus cotangent of inverse sine x over 3 minus inverse sine x over 3 plus c. How you like me now? All right, these are a little tricky. And there's one last thing which I might want you to do. In my opinion, this is a fine answer, but actually, I will say if we want, we can simplify cotangent of inverse sine x over 3. Anybody remember how to do that? This is something we talked about back when we were doing these inverse trig functions. You have to work it out a little bit, but anyone remember how to set that up? Yeah?
Sine of what equals x over 3.
And then you do the
that,
cotangent.
and you put that
Yeah, so for this I would draw a little triangle where the sine is x over 3. So like here's the angle I'm talking about. I want the sine to be x over 3, which is to say the opposite over adjacent is x over 3. So this is x and this is 3. So that angle is now inverse sine of x over 3, and then I want the cotangent of that triangle. So that would be, you have to find the other side first using the Pythagorean theorem. This side would be 9 minus x squared by the Pythagorean theorem, and then I do the cotangent of that. So cotan of inverse sine x over 3 is actually cotangent is adjacent over opposite, right? It's the reciprocal of the tangent. So that's this divided by that. So this is 9 minus x squared over x squared. Not x squared, x on the bottom. That's the cotangent of that angle. And so, having done that, my sort of real and true final answer. Now this, if I wanted you to do this on a test or something, I would tell you. Like in my opinion, that what you say at the top is a perfectly fine answer. Although I might say something like, simplify as many inverse trig functions as you can. Now there's nothing you can do with that. You just have to leave that like it is. But this one you can simplify. And so my sort of well and truly final answer is this. That's the first part, minus. This has to stay like an inverse sine. I just simplified that cotangent of inverse sine part. Yes?
Does that 9 minus x squared have to be under a square root? Like,
Yeah, because of the Pythagorean theorem. Did I mess that up? Yeah, so I should have said x squared plus, if I call this a, not a, I use a for something else. I'll call this one b. X squared plus b squared equals 3 squared. Yeah, you're right. It should be a square root. Thank you. Like that. Sorry, I messed that up. So that's here and here. Thank you for that. Even better. All right. This is the trigonometric substitution. I have one more, and then I have one for you all to try. All right. My one more is based on a variation on this. So you should, if you're keeping score here, you should try and keep track of these tricks. So if I see, this is the one we just did. If I see that, square root a squared minus x squared, this, I should do the substitution x equals sine theta. And of course that means dx equals cosine theta, d theta. It turns out for similar reasons, and we'll just work one out. If you see this with a plus, a squared plus x squared, you should do x equals, sorry, I left the a out. I was trying to summarize here. It's a sine theta and a cosine theta. Anyway, when you see the square root of a squared plus x squared, the correct substitution to use is x equals a tan theta, and dx is a secant squared theta d theta. It turns out that makes it all happen for examples with a plus under them. And let's just try one example with a plus under the square root, and then I have one for you all to try. How about 1 over x squared and then 25 plus x squared dx. So as far as like things that you have to more or less memorize to make these tricks work, it's really just this, right? These are the formats that you need to remember in terms of which substitution am I supposed to do in this or that example. All right, let's try it. So I see, first of all, I see a square root with a thing squared plus another, plus an x squared. So I'm going to use the tangent type substitution. So I'm going to do x equals, what's the a this time?
5.
5, yeah. X equals 5 tan theta, which means dx is 5 secant squared theta d theta. All right. Let's go over there and plug everything in as best as we can. X squared down there is going to be 5 tan theta squared, and then square root 25 plus 5 tan theta squared. And then dx is 5 secant squared theta d theta. Right? What next? What do you think?
Square 5 tan. Square 5 tan.
Okay, square out the 5 tan thetas where you see them. 1 over, so this is going to be 25 tan squared theta. And then over here, 25 plus 25 tan squared theta, and then 5 secant squared theta d theta. All right? What else?
Take out the 25.
Yeah, pull the 25 out of the square root in the bottom. That makes it a just a 5, but it's in the denominator still. So this becomes 1 over 25 tan squared theta times 5 square root 1 plus tan squared theta. And then over here, 5 secant squared theta d theta. All right? Unfortunately, these 5s and 25s don't all cancel out. You just get the 5s cancel, I guess, and you end up with a 25 on the outside. 1 over 25, I'll pull all the way out of the integral. So this becomes 1 over 25 out front. And then what I see on the inside, 1 over tan squared theta. And then this is square root 1 plus tan squared theta. And over here, secant squared theta d theta. And what is the point of all this? 1 plus tan squared. The point of this is 1 plus tan squared. This is another trig identity. This is secant squared theta. This is the identity that goes along with cosine squared plus sine squared equals 1. Tan squared minus secant squared equals 1. All right, and so when we plug that under the square root sign, we take the square root of the secant, and the square root of the secant squared becomes secant. So this is, sorry, I didn't draw the integral sign. I don't know why. 1 over 25 integral 1 over tan squared theta secant theta secant squared theta d theta. Getting anywhere? Maybe. All right. Now, at this point, if I didn't know any better, I would just maybe try and simplify all of this by writing tan as sine over cosine and secant as 1 over cosine, and sort of hopefully a lot of those things will cancel and recombine in some way. Actually, because I know where this is going, I'm going to do a special little trick here. This kind of a trick you might come up on the homework, not on our quizzes. 1 over tan. So first of all, the secants can kind of cancel. There's this one secant on the bottom and one secant up top. So those cancel, and I just get one secant in the numerator. And then this 1 over tan squared, I'm going to write as cotan. Sorry, this is not what I wanted to do. I think I will write them all as sines and cosines. I'm trying to do too many steps in my head here. This tan on the bottom, well, I'll say first of all, secant theta over tan squared theta, right? Cancel one of the secants, and this is what you end up with. Secant squared is 1 over cosine. Tan is sine over cosine. So if you work out all of those various sines and cosines, I believe what you end up with is sine squared, no, it's sine squared on the bottom. The secant is 1 over cosine, right? And then the tan on the bottom, the tan is sine over cosine, but it's in the denominator, so I'm going to write it as cosine squared over sine squared, right? There's many ways you could think that through. That first one is the secant, and then the second one is the reciprocal of the tangent squared. Some of these cosines will cancel, but not all of them, so it says 1 over 25 integral cosine up top over sine squared theta dx. Anyone got a suggestion here? Yeah?
You can rewrite it as cosine over sine, 1 over sine, which is just cotangent cosine.
Yeah. So I have two options for you, actually. I don't know if you'll like either of them. One is to do what he just said. This cosine over sine squared can be rewritten as okay, if you pull out one of those sines in the denominator, you can write it like this. 1 over sine theta, and then the other would be cosine theta over sine theta. Why do that? It's because this is now cosecant theta times cotange theta, cotange. And what is that? He apparently likes it.
It's the integral of something. Right?
Yeah, there's an integral formula for the integral of cosecant times cotangent. This is it's
Cosecant.
I think it's negative cosecant. So this is another one of those, look up this formula. Negative cosecant theta plus c. And now we are pretty much done here. I said I had two ways of doing this, and you're not going to like either of them. The other way is right here you can do a u substitution. U equals sine theta, and then the du is cosine theta d theta. And so what we have here is 1 over u squared du, which you can integrate that way. All right, anyway, can we just finish off this right here? I should rewrite in terms of the original variable. So the original variable was x, remember my original substitution? X equals 5 tan theta. So to solve for theta here, I would divide 5. X over 5 equals tan theta. And that means theta is inverse tan of x over 5. And so my answer here can turn into 1 over 25 times negative cosecant inverse tan x over 5 plus c. All right. I can tell by the looks on your faces, you are loving this. This is complicated, in my opinion. And this is, I would say, as far as like doing weird tricks in a weird sequence, this is maybe one of the hardest things that we're going to do this semester. We're not going to do a lot of stuff like this, but this is In this section, this is what it's about. All right, I got one for you all to try. We got 20 minutes left. Certainly that will be enough time to try one all together. If you dare, let's try integral x square root 4 minus x squared. And I'm gonna say, oops. Simplify as many inverse trig functions as you can at the end. That's what I did not do in this previous example. I left as cosecant of inverse tan, but you can further simplify that. It's not messed up. How's it going? Yeah, it's good so far. Yes, and I. Oh, I should. What you want to see is our e squared minus x. And then now you're going to split. Yeah, that's the variable. Now you're going to square this. Substitution. Yep. And there's, yeah, but you need to put that for x there also. Yes. You see what to do next from there. If you have square root with two things added together, it's like you can't just like do separate, but you get something. Good here. Yes. Hold on. Oh, because this is just good here. That's how it started.
And you get to here. And this is like.
Mm-hmm.
And then you like use one of these identities.
I would actually just from here, you can do substitutions. Use the time. How's it going? Uh-huh. This 4, when you bring it out, can get 2.
Oh, okay.
Good here?
Do you do this or do you just do use it?
I would use
They don't cancel.
because one of the parts is ours. How's it going? Mm-hmm. Yep. Up here. Something is still. But then it's a zero gap. This is all good, although it's.
Could I do that?
It's through.
The 1/2 thing, that is, I don't think that's very helpful. Yeah. You can, right here, it's just. So this F is. This X is straight up supposed to.
Okay.
I'm not sure what that's. Yeah, when you pull this 4 out of this way. Right here? You got an answer. I don't remember. Doing good here?
I think so. Does that look
Great,
right?
yeah.
What do I do next?
Here,
No.
this is like one of those trigonometric intervals.
Oh, okay.
I have.
Oh, right.
So you can do your substitutions.
Wait, so like, does this look like right?
How's it
process?
going? Yeah, yeah, that looks pretty good. I don't know if that's exactly right, but something like that.
I think, I don't know.
So like,
The only thing is the cosine
I would
should be
say from
for at the
here.
very bottom.
What did you guys get?
it's at the very bottom?
After you do the use of, do you get sectors?
Yeah, but
Yeah, you got that, okay.
You can just
And then,
do that to
oh,
the
substitution.
You
And then
just
you just need to plug in that data, yeah.
wait, he said to put it like,
I think here you didn't have.
you know churn really well.
This is, there's no close.
There's no simplifying cosine fusion.
Oh, there is.
No, not like an identity.
No.
Since there is a
Yeah.
cosine, it means you can do it. That's weird.
If you're simplifying like the whole thing, why don't you just take like the actual cosine cubed if you have
Yeah,
a
this is good.
triangle?
Yeah, these 4s can come out and it becomes.
That's a good question. I think the only thing you forgot is your D. You have to multiply the D.
The BU?
Yeah.
I don't even know. I'm lost. Like, I don't know if
Like this.
Alright,
Like this.
alright.
So I wouldn't have done that. Here you have cosine squared.
Yeah.
So this, I would take the constants out.
Okay.
Sine theta times cosine squared theta. And that you can do use substitution.
Oh. Okay. Alright. Okay.
Is this correct?
Maybe. I don't remember exactly what the answer is supposed to be, but something like that. Although you should do what I said. It simplifies many inverse strings.
How do you do that for the cosine cube?
You just do the cosine and then the.
Or is it something like this when you like?
Yeah.
Find
Uh-huh.
this?
Yeah. How's it going here? I think you lost the square root sign somewhere.
What's a derivative sign is derivative of cosine is negative sign, right?
Yeah.
Or
Sorry,
negative sign. Alright. That was
Yeah.
Wait, did you get a final answer after you?
All right, let's try this one out. We got about 10 minutes remaining. I think we can just finish this off and that'll do it.
Yeah. Cube.
So I did x equals 2 sine theta.
We got the same.
Everybody did this, really.
Just smart, honestly.
Dx is 2 cosine theta d theta. So it says you have to plug in for all the x's. So I'm going to have 2 sine theta square root 4 minus 2 sine theta squared, like so. And then dx is 2 cosine theta d theta. All right, square out the thing in there. I get square root 4 minus 4 sine squared theta times 2 cosine theta d theta. And then those 4's can pull out of the square root sign and become a 2. 2 sine theta square root 1 minus sine squared theta 2 here, and then 2 cosine theta d theta. So I think all the constants pull out and give you an 8 in the front. I have 3 2's there. I got an 8 in the front, integral sine theta. That square root, 1 minus sine squared on the inside, is cosine squared. So this is square root cosine squared. That's going to be a cosine. And then another cosine at the end. So we got 8 integral sine theta cosine squared theta d theta. And this, I would say, is the end of like Act 1. At this point, I hope that you made it to this point, and then you will temporarily get stuck and say, what am I supposed to do with that? The way that I would consider this is this now looks like one of those trigonometric integrals of the type that's on the homework for tonight, for example, where I have one even power and one odd power. And the thing to do in such a situation is you just do a u substitution. Here, u equals cosine theta. du is sine theta d theta. That's the appropriate trick when you have products of trig functions with at least one of the powers being odd. You do this kind of a substitution. That's what I call the save one trick, although one of them is already saved. That sine theta becomes the d theta. Right? So doing that substitution, I get 8 out front. And then really, what is it when I write that in terms of u's?
For sine, this would be derivative of cosine, so negative sine of sine.
Oh, did I do the, yes, I did the derivative wrong. Thank you. Minus sign instead of positive sign. Thanks. Anyway, what's it look like when I write this in terms of u's?
U squared.
Yeah, it's u squared and then times negative du, right? There will be a minus sign in there because of this derivative of cosine is minus sign. I think some people are giving me encouraging looks, some discouraging looks. That's all right. This is a safe space for you to express your disapproval. All right. Then, okay, let's just pull the minus sign out. Minus 8 integral u squared du. Do the integral. This is an easy integral now. 1/3 u cubed plus c. And now write this in terms of the original variable. Actually, I'm like 2 substitutions deep here. First of all, u is cosine theta. So this is minus 8/3 cosine theta cubed. Like that, right? And then to unravel the theta substitution, remember theta, what was defining theta? My original substitution was x equals 2 sine theta, right? And if I'm going to plug back in, I need to solve for theta. So this says x over 2 equals sine theta, which means theta is inverse sine x over 2. So this is minus 8/3 cosine of inverse sine x over 2. All of that cubed. All right, and this is pretty good, but I said specifically at the beginning, simplify all of the inverse trig functions in your answer. So I need to simplify cosine of inverse sine of x over 2. And to do that, I draw a little triangle where I want the sine to be x over 2. That's x over 2 like that. The sine of this angle is now x over 2. And then we find the third side using the Pythagorean theorem. So if that's b, then this should be, well, it should be x squared plus b squared equals 2 squared, which is 4. And solving that for b would be square root 4 minus x squared. And then finally, I take the cosine of that angle, which is the adjacent, that square root thing, over the hypotenuse, which is 2. So this is my well and truly final answer. Adjacent is 4 minus x squared over the hypotenuse, 2. Anybody actually get that the first time around? I hope so. I saw a lot of variations on this as a general theme. If you got it, great job. If you got close, also great job. It's not easy to do it completely right. All right. I think based on the looks on all your faces, we should call it a day right now. See you next time. Check out